first of all, thank you for giving me the opportunity to present on such a big platform. I'm so humbled to present here. And also the last speaker, Angelina, the presentation was so awesome. You definitely got me interested in learning Chinese right now. So now, first of all, I'll make an introduction to our model, and then I'll give an introduction to our team members. So as you all know, my slide is clearly visible, right?
Yes. Yes.
Right. So this is GesSure. GesSure is a smart step towards automation, and it provides accessibility to manipulate our laptops or PC and manipulate daily tasks. So basically, it eases the user access on our personal computers. Now, it comes under the bucket of smart automation because it improves human-computer interaction. Now, the importance of contactless communication became very evident in the post-pandemic world just after COVID. And the lack of user authentication in existing gesture recognition systems, however, renders them really insecure. Additionally, static movement hinders user compatibility, and they also require lengthy adaptation times in the current generation of gesture detection technologies. So we thought about developing GesSure. This was the incentive behind the project. Now, user recognition, security, and safety are the top priorities for this technology. And for task execution, we have employed very meaningful and senseful gestures, which helps us in improving the user's experience. And the ultimate goal of this work is to design a reliable face-verified gesture recognition system with a very good graphical user interface that primarily emphasizes user recognition and authorization for the security purposes. So now I'll give a brief introduction to our team members. So first of all, I'd like to mention Ankit. He is a fourth-year engineering student in Manipal Institute of Technology, which is in India. And then comes me. I'm Ishita. I'm a third-year engineering student, hailing from Electronics and Communication Department, again from Manipal Institute of Technology. Next off is Ayush Batra. He's also a third-year engineering student from the Computer Science Department. Next, Piyush Modi. He's also a third-year engineering student from Electronics and Communication Department. Next is Pratham Shenwai. He is also third-year engineering student from Aeronautical Department. And last off is Siddharth Kotian. He is also in third year and in Computer Science Department. So we are probably the youngest here. Now, giving an introduction to our model. So now, again, as I already said, that in the post-pandemic world, it is very important for us to have a very good gesture recognition system. And I think I already gave a very brief introduction about the system. So I'll just move on to the data set. So now we did not use any existing data set, which is already available on the internet. Instead, we chose to create our own data set. That was because we wanted to make the system very robust, and in future we wanted to give the user the ability to choose his to create his or her own data set. So we started with doing it. So first of all, for face verification, I'll speak about both face verification and gesture detection. So starting with face verification. So we created our data set using OpenCV and used it to verify faces. Each individual can record for 20 frames, and the wait key was given 500 milliseconds. And to attain the highest level of precision as a trade-off, as many angles as were feasible were taken to help the model distinguish between the faces of the verified users and the stray users. We made a separate new category called stray users, where random faces were stored, like random people's faces were stored. So the model does not confuse between stray users and the verified ones. Now, we have used only one user. Only one user is verified as of now for our assignment. However, in future, even now, you can verify multiple users. So now moving on to the dataset for gesture detection. So the dataset contains of 5 static movements that were taken from 4 different people, and they were stored as NumPy arrays. To improve the model's ability to identify random gestures, again, a new category of random gestures has been taken. So now each move was again captured for a total of 20 frames, and we trained our model using the combined data. The tech stack we used for this gesture detection dataset making was NumPy, Matplotlib, OpenCV, and MediaPipe packages. Moving on to the architecture for face verification. Again, the architecture part has also been divided into face verification and gesture detection. So moving on to face verification. So focusing on popular deep learning techniques, we actually performed softmax classification, FaceNet feature extraction, and MTCNN face identification. So we combined all three of these to give the best performance possible. Now, to identify faces and other facial landmarks in photos, a neural network known as MTCNN or multi-class cascaded convolution neural network is utilized. A deep neural network called FaceNet has been used to recognize facial traits in the photos and videos of the people. And MTCNN was again used to identify the faces of the input images, and FaceNet was used to create the face embeddings of the people, of the images. Right, this is just a continuation of the previous slide, that is architecture of face verification. So moving on, explaining it in more depth, FaceNet, we use FaceNet as I mentioned. So FaceNet takes a photo as an input and outputs a 128 number facial embedding vector. Now this embedding incorporates key facial features of the input image. And the embeddings produced by the FaceNet can be used to plot a picture in the Cartesian space. So for unseen face photos, models often try to create face embeddings, which they can contrast with trained data, which is already made. So the class with the embedding representation that most closely matches the testing images receives the final allocation. So that way we have made sure that the accuracy of the model is maintained. Now, FaceNet acquires the facial data in majorly 4 ways. So the first way is to choose an anchor picture at random. Second is to pick an image of the same subject at random to serve as the anchor image. Thirdly, it chooses a person's image at random that isn't the anchor image. So that comes under the bucket of negative example. And fourthly, modifies the FaceNet network parameters to place the positive example nearer to the anchor and the negative examples far away from the anchor. Right. So a positive and negative instance and anchor and a learning approach called triplet loss is used here. So depending on the use case, classifiers like KNN, softmax, we have used softmax over here, random forest and SVM are given the FaceNet's output embeddings. Because softmax can function effectively for neural networks, we have employed it. So that was about the architecture of face verification. Moving on to the architecture of gesture detection. So again, this is the architecture of gesture detection is further divided for the simplicity of understanding into two parts, that is detection and localization of hands. And again, first of all is the detection and localization of hands, and this slide is the continuation of the previous one. So now moving on. So for detection and localization of hands, we have used an open source library called MediaPipe. So this framework, MediaPipe, it enables programmers to create multi-models, cross-platform applied ML pipelines. They use the skeleton of nodes, edges, or even landmarks to track important locations on various body components. Like to demonstrate, if this is my hand, then it has 21 coordinates that are already defined by the makers of the MediaPipe framework. So similarly, they have landmarks for face verification or even posture detection. So right, we have used MediaPipe pipelines here. So okay, moving on, every coordinate point has been normalized in 3 dimensions, and models for palms and hand landmarks detection make up the backend machine learning pipeline of the hand tracking system used here. And additionally, the landmark model receives a precisely cropped palm image from the palm detection model. And the data augmentation techniques used in deep learning models, such as rotations or flips and scalings, are reduced by this approach, which concentrates the majority of its strength on landmark localization. Now, using the ML pipeline in this palm detector puts a different approach to test, since we must perform image processing, thresholding, and work with different hand sizes. Detecting hands is a really time-consuming process, so that can make the system less robust. So instead of immediately recognizing hands from the current frames, the palm detector is first trained. So this method is simpler than detecting hands with connected fingers, since it estimates bounding boxes around strip objects like your palms or like even your fists. So a bigger scene context is extracted by an encoder decoder tool. Subsequently, hand landmark models appear in the images after palms are detected over the full image frame. So within the detected hand area, this model precisely locates to 21 3D hand knuckle coordinates that, as I mentioned, there are 21 coordinates in here. And again, the model can detect hands with great accuracy and reliability, and it can map hand coordinates to hands that are only even half visible. Like even the hand is half visible, it will give the landmarks. Now, given that we have a functional palm and a hand detection model, we can ask the user to demonstrate the gestures before the camera. So now this is the overall architecture we have used. So we have used basically 2 convolution layers, 1 LSTM layers, 4 dropout layers, 1 time distributed layer, and 1 thick layer makes and 1 thick layer make up the proposed deep convolution LSTM neural network. So rectified linear unit is used as activation layer in the convolution and LSTM layers, while the function is used in final dense layer. So we have trained a total of 237,718 parameters. With a 3x3 initial convolution layer, the architecture gets started. We estimate the input size to be 20 by 63. Since the gesture is composed of 20 frames, as I mentioned before, obviously you can change it. Each of which contains the X, Y, and Z coordinates for each of the 21 landmarks that are available in the palm, which is detected by the MediaPipe. The most noticeable features are extracted from the output using a max pooling layer with the pool size of 2. After that, a dropout layer is used to lessen data overfitting so that the data does not overfit and the model can be used in more generalized sets. So a set size of dropouts of 25% exists. The dropout is then sent via a dropout layer, a max pooling layer, and again a comparable convolution layer. The output from the layer mentioned above is routed through a time distributed layer, which I mentioned before, which enables us to layer each output's individual temporal slicing. This layer enables us to feed the LSTM layer with the output from the convolution network layers. So 200 neurons in total make up the LSTM layer, which rectified linear units serving as the activation function. We have only employed, as you can see here, we've only employed only 1 LSTM layer, since we were able to obtain a considerable level of accuracy with only 1 layer. So it eliminated the necessity to incorporate further LSTM layers. And a dropout layer of 0.25 size is added after it. At last, we cross the output through a dense layer with softmax activation function again. This was about the identification of hand gestures. Now, moving on to the GUI approach. As I mentioned before, we wanted the system not to be only technical, but also user-friendly for the user. So we have made a very nice and good GUI for the ease of user's access. So the prototype from GesSure employs a training and in-use strategy. So the basically the training strategy is when a new user tries to record, and the in-use strategy is when the user is already registered and is using the system for the second or third or more times. Right. So first of all, the face verification model must be trained to assign the designated user tag during the training phase. So like for example, if you're using it for the first time, so we want you to register your face. So the face detection model then registers your face, and you are assigned the tag of designated user, right? So and that is a requirement that is necessary to do for the first time. Then the model captures 20 photographs. Ideally, you should make the photographs from different angles so that the model is again more robust, and then we store them in a user directory, which sets the path as the verified user. Now, this process records the individual spaces. After that, the GUI offers a user interface so that the users can record or employ their own pre-trained models. So not just our 5 models, which we have already implemented, you can make your own gestures. So if we have already assigned the macros, right now we have them for undo, redo, scroll up, scroll down. So you can, to the assigned macros, you can assign your own gestures. So we have given the user that visibility. Also, the macros can further be increased in future. That is a future prospect right now. So now the yeah. So additionally, existing tasks can be assigned to the gestures as macros again. The dynamic gesture offers a better user experience by allowing the intuitive gestures, which frees the users from having to recall predefined gestures. So I hope we are very clear with the definitions of static and dynamic gestures. So now, like if I put on my two with 2 fingers on my screen, so this is a static gesture. Now, if I wave my hand across the screen, that is a dynamic gesture. So dynamic gestures are obviously more intuitive, and we have that incorporated in our model as well. So the prototype's current macro options, which are already pre-trained, are a save, quit, print, screen lock, and restart. So, for example, if you're using Microsoft Word, I hope everyone is very comfortable with Microsoft Word. So you can just use gestures to save the word, save the changes in your Word document, or to exit the Word document, to print the Word document. So for all this, you can just use the gestures instead of using your keyboard. So, and then the current applications are affected by the context of save, print, and exit procedures. So for instance, saving a Word document with the save gesture, opening the printer dialog box with the print gesture. Similarly, we have assigned the gestures to exit and exit command, which closes the current application. So in the absence of any open applications, the macro, which has been, the gesture which has been assigned for a shutdown, the gesture which has been assigned to close the application will also shut down the system. So the user can toggle a button to activate the gesture prototype during the in-use phase. And the face verification models developed during the training phase is used in the prototype as a security overlay with identified users' photographs. Only once the user's presence has been confirmed by the face verification algorithm, the gesture algorithm can work. So the algorithm uses one-shot learning, and then it uses FaceNet, MTCNN to recognize faces and extract facial features, as well as, again, a softmax classification layer to classify faces. And the duties given to the trained gesture motions can now be controlled by the confirmed user. So in this case, we combine CNN with LSTM. And to extract spatial characteristics, we have employed 3 convolution layers here, one-dimensional and two-dimensional. And since LSTM layers are effective at retaining information from both the previous and the current frames, we employ them to extract temporal features. Since the LSTM model is considerably lighter than the GRU1, we have used it instead of the GRU1. So dropout layers make the model appropriate for widespread use, and it again prevents overfitting. So this was about the GUI approach. Now discussing the results of our model. So first of all, I'd like to discuss it in terms of the face verification. So as you can see, by the way, these are 2 of my teammates. This is Ayush Batra on the right, on the left, and Piyush on the right. So a non-registered user is, so here the registered, as you can see, Ayush here on the left has not been registered. So he has been identified as not verified, and the accuracy is given here with the accuracy with which the user is set to be non-verified. And again, Piyush here is a verified user, so verification completed. So similarly, a non-registered user is labeled as a stray user by the face verification model, and it achieves good accuracy. So when the user detection accuracy is greater than 90%, the application only then activates the gesture recognition model. So the threshold of 90% has been set by us, so that so again for the security overlay. Right. So if there are numerous people in a frame and the user is one of them, the model will still accept the user. Like for example, if Piyush and Ayush here were in the same frame and Ayush is not detected, but Piyush is verified, the model will still work because Piyush is again in the frame. So this was about the face verification model. For the gesture detection, the gesture detection model. It uses MediaPipe again, and it has achieved an accuracy of 95% on the 5 gesture classes. So the thing to note here is it achieves 95% of accuracy on the small data set that only 5 people created. So that is a big achievement in itself. Now, for going on to the results for task manipulation. By the way, the ones you see here are the pre-trained gestures right now. So this is for save, then the C for close window, then this V for print, this is lock workstation, and this is restart. Right. So we practiced the 5 motions and gave them each a macro job to complete, like macro jobs like face and close window. And activities can be divided into 2 main categories, that are context-dependent tasks and context-free tasks. So application level activities can be started by gesture and context sensitive tasks. So we integrated gesture triggered actions like save, print, and quit to Microsoft Word. We included functions like, similarly to Microsoft Word, we have also made it to VLC Media Player also. So in VLC Media Player, we have macros like play and pause, and then the volume control, and then you can move forward 10 seconds or even backward 10 seconds using the same macro. So gestures can initiate context-free actions that are connected to operating systems, such as, again, the last 2, restart and lock workstation. So this was about task manipulation. Discussing the conclusion and future scope. So the development of successful human-machine interactions has been substantially impacted by the hand gesture recognition systems. Such devices are an accessibility help for people with disabilities who can communicate via hand gestures. So systems for hand gesture recognition currently have some drawbacks. So such as they lack integration for an authentication check, and that makes them really dangerous to use, because just imagine someone else getting an access to your computer. That is really unsafe. So additionally, they employ only static gestures similar to those in the American Sign Language. So it gives a burden on the user to remember those hand gestures, and the system is really less intuitive. So we have tried to cover up all these drawbacks, making the system more secure and safer for the user, and to make the systems and to make the gestures more intuitive in our prototype. So in this article, the development of the prototype of the user authentication integrated HCI system was the main focus. And the system uses a gesture recognition system to let users manipulate frequently used context-free and operating system tasks. And we have employed meaningful and potent gestures for tasks rather than aiming for difficult to memorize and easy to compute and classify. So the other option was like, we can ask the user very random gestures which are easy for us to compute. So we have not done that. We have made it more user friendly, so that it provides a better user experience at the end. And this was the conclusion. Discussing the future scope. Future scope will focus on improving the prototype's extensibility, UI, and development of an ad, and making it as a whole package that can be open sourced and it can be downloaded and can be used on various operating systems. And we can also extend the system beyond individual computers. The user experience for people with disabilities can be improved by integrating these gesture assistance technologies into, for example, ATMs. And another example is, again, automated dashboards in cars, which can allow for user interaction while reducing the need for physical contact, which we think will be really good for reducing road accidents. So that was the end of my slideshow. I'll end the slideshow here.